glycolysis is going to start with glucose. And glucose is going to undergo a series of chemical reactions, ultimately producing fructose 1,6-bisphosphate. Now, fructose 1,6-bisphosphate seems like a big word, but what it really means is this. Fructose has 6 carbons, just like glucose does. Fructose has 6 carbons, and they are numbered 1, 2, 3, 4, 5, and 6. Bisphosphate means 2 phosphates. One of the phosphates is going to be on the first carbon of fructose, and the other phosphate is going to be on the 6th carbon of fructose. Now, in order to get this chemical reaction to occur, we're going to have to add some energy. Notice that I drew another arrow. These are referred to as coupled reactions, meaning we're going to have more than one reaction take place at the same time. And it's an all or none process. Either both reactions take place or neither takes place at all. So I'm going to take 2 ATPs, put the energy in, and out are going to come 2 ADPs plus 2 inorganic phosphates. So I'm going to use energy to get this process going, and ultimately we're going to get a whole lot more energy out. Now, fructose 1,6-bisphosphate is going to break up into 2 molecules of pyruvate or pyruvic acid. And again, we have a series of chemical reactions. I'm just showing some of the molecules. Now, what we're going to get out here is 2 ATP. And the same thing is going to occur on the other side. To 2 ATP. So ultimately I get 4 ATP out. In addition to this, I'm going to use a carrier molecule, NAD+. It's going to come in and it's going to pick up its cargo, 2 high energy electrons and a proton. That cargo ultimately came from fructose 1,6-bisphosphate. Now when NAD+ picks up its cargo, it's going to get reduced to NADH. And again, the same thing is going to happen on the other side. The first part of this is referred to as the energy investment phase, because we had to put energy in to get it to happen. So that's going to be the energy investment phase. And the last part is going to be the energy yielding phase, because that's where I get energy out. Now this whole process is going to take place in the cytoplasm. And the energy in is 2 ATPs, and the energy out is going to be 4 ATPs and 2 NADHs. When we're all done, we're going to tally up all this energy. Also, we want to keep track of carbons. Glucose has 6 carbons. So, all right, 6C, 6 carbons. And fructose 1,6-bisphosphate also contains 6 carbons. When we break this molecule up, we can't gain or lose carbons. So each molecule of pyruvate is going to contain 3 carbons. Now pyruvate is ready to enter the next set of chemical reactions. And the next set is going to be the gateway reaction. And the gateway reaction is going to begin with pyruvate. I'm only going to draw one molecule up there, but understand that both molecules that we produced here from one molecule of glucose, both molecules of pyruvate are going to undergo this series of chemical reactions. In addition to that, this pyruvate has to be transported into the mitochondrial matrix. That's where the gateway reaction is going to take place, in the mitochondrial matrix. And it's going to cost us 1 ATP per molecule of pyruvate that I transport into the mitochondrial matrix. So I'm going to write another -1 ATP because I have two pyruvates that need to be transported into the mitochondrial matrix. From there, the gateway reaction is going to occur. So the gateway reaction begins with pyruvate, and it's going to end with a molecule called acetyl-CoA. CoA stands for coenzyme A. So acetyl-CoA. Now, in this chemical reaction, a carrier molecule, again, NAD+, is going to pick up two high-energy electrons and a proton from pyruvate and is going to be reduced to NADH. Okay? NADH is our loaded truck. It's carrying enough energy to ultimately produce 3 molecules of ATP. Now, if we keep track of the carbons again, pyruvate has 3 carbons. And in this chemical reaction, we're going to lose a molecule of carbon dioxide. And carbon dioxide has 1 carbon. So 3 carbons minus 1 carbon we lose here in the form of carbon dioxide is going to give us 2 carbons for acetyl-CoA. Now let's tally up our energy that we produced with a gateway reaction. We produced 1 NADH, and another pyruvate is going to produce another NADH. So ultimately, we're going to produce 2 NADHs. From there, acetyl-CoA is going to go into the next series of chemical reactions called the Krebs cycle. And it's a cycle, so think of it as a circular series of chemical reactions. Ultimately, what we end up with is going to be used to start the process again. That's why it's called a cycle. So we're going to start with molecule number 1. I'm going to write that over here. Molecule number 1, 2, 3, 4, 5, 6, 7, and 8. And I'm going to connect up these molecules. Molecule number 1 is referred to as citrate. Hence the name, the other name for the Krebs cycle, the citric acid cycle. Citrate or citric acid, same thing. Acetyl-CoA is going to come in and join molecule number 8. And together they're going to form molecule number 1, referred to as citrate. This process also takes place in the mitochondrial matrix, so it doesn't cost us any energy. Okay. Now molecule number 2, we're going to call it just molecule number 2. All these molecules have names, but they tend to be complex names. And this is probably the most important one, citrate and acetyl-CoA. So let's just remember those. Now, acetyl-CoA comes in, joins molecule number 8, to form citrate. Citrate then undergoes another series of chemical reactions and forms molecule number 2. Now this is where we start to produce some energy. Molecule number 2 then undergoes a chemical reaction, and a carrier molecule, NAD+, comes in. It's reduced to NADH, so it picks up 2 high energy electrons and a proton from molecule number 2. At the same time, we're going to lose a carbon dioxide. Molecule number 3 is then going to undergo a chemical reaction to form molecule number 4. At the same time, again, another carrier molecule, NAD+, picks up its cargo and is reduced to NADH. Just like before, we're going to produce another carbon dioxide molecule. From here, molecule number 4 undergoes a chemical reaction, and we're going to produce ATP. So I got an ADP plus a phosphate going to ATP. So we produce energy that we can immediately use right now. Molecule number 5 is now going to get converted to molecule number 6. In doing so, we're going to produce some energy. We're going to have another carrier molecule called FAD come in here, pick up its cargo, 2 high energy electrons and a proton, and get converted or reduced to FADH2. Molecule number 6 is now going to get converted to molecule number 7. No energy produced there. However, molecule number 7, when it gets converted to molecule number 8, we are going to pick up some more energy. And NAD plus is going to be reduced to an NADH. However, no carbon dioxide is going to be produced in this step. Now think about this. We have 2 carbons in the form of acetyl-CoA coming into our Krebs cycle. And you can see here we lose a carbon dioxide, so we lost 1 carbon there. Here we lose another carbon dioxide, so we've lost another carbon there. So 2 carbons in, 2 carbons out. We also produce quite a bit of energy here. Remember, we have 2 acetyl-CoAs coming into this cycle, so there's going to be 2 turns of this cycle. So I produce an NADH, 1, 2, 3. And because I have 2 turns of the cycle, 3 plus another turn, 3 more, ultimately I'm going to get 6 NADHs. Same thing goes with ATP. I produce 1 ATP here, but when the other acetyl-CoA comes in, I'll produce another ATP for a total of 2 ATP. FAD goes to FADH2. I've got 1 of those, and when the other acetyl-CoA comes into my cycle, I'll produce ultimately 2 FADH2s. Now, what we want to do at this point is tally up all our energy. So let's go ahead and tally up our energy. We're going to start with glycolysis. We produced 4 ATP with glycolysis, 2 NADHs, and no FADH2s. Now we know that FADH is a carrier molecule and it's carrying enough energy to produce 3 ATP. So I'm going to write times 3 equals 6. 2 NADHs, each capable of producing 3 ATP for a total of 6 ATP. Now when we add these numbers up, 4 plus 6, the total amount of ATP that we'll ultimately produce when this is all said and done is going to be 10 ATP. If we do the same thing for the gateway, we find out we produce 2 NADHs, each capable of giving us 3 ATP, so 2 times 3 equals 6, and we're going to have a total of 6 ATP. And Krebs cycle is going to give us 2 ATP immediately, 6 NADHs, each capable of giving us 3 ATP for a total of 18, 2 FADH2s, each FADH2 is capable of producing 2 ATP for a total of 4. So let's add up our numbers. 2 plus 18 is 20, plus 4 more is 24. Let's add these all up and call it our gross ATP. So 24 plus 6 is 30, plus 10 more is 40. So 40 ATP gross. However, that's not my profit. If you recall, I had used 2 ATP to get glycolysis going, and then 2 more ATP to transport each pyruvate molecule from the cytoplasm into the mitochondrial matrix. So I'm going to go ahead and keep track of that. Minus 2 ATP for glycolysis, and minus 2 more ATP for active transport. I'm then going to add everything up. 40 minus 2 more is 36 ATP. And I'm going to call this my net. That's my profit right there. I have a profit of 36 ATP, which is pretty good.